I would recommend everybody to watch or to revisit the materials we already have so far from the 3300. Okay. And I would like actually to congratulate all of those guys already have a great achievement. And also, for the other people, I have a very good offer. What is this offer? If you like to do more and better than what you have, so the quiz number 2, if your grade is higher than the old one, I will match it. So let's say that quiz number 1, you got 60 out of 100. Then quiz number 2, you get 80 out of 100. Then you know what I'm gonna do? I'm gonna give you 80 in both. But let's say that quiz number 1 you got 100, but then quiz number 2 you got 50, right? Then I will not match it. If I match it, it's gonna be a big mess for you. So then I'm gonna just put your grade as it is. Sounds fair? Same thing for midterm, yes. So let's say that Sean, let's say that you got in midterm 70, right? But then you came in the midterm 2 and you got 100. Then you're gonna have 100 in both.
I follow what you're saying, Professor. Thank you. I just wanted to know if you were doing.
No. I just want to clear it up for you guys. So basically, no, I'm trying here to help. I know that it's really hard time, and I know that it's really quite difficult for for you and for me as well. All of us working through a bunch of wires. So anyway, but at least what we can do, we will try to do the best from both sides, right? So I will start go through the midterm with you, and I clarify that how it works and what is expected answers and so on. And then you will do your best, but you need to promise me to go and revisit all the material I shared with you, because most of the midterm one, it was coming from the material. And I believe that I talked about how can you calculate the critical path and stuff like that, right? So just revisit it and see what is the best. Another questions. Last midterm, I made the time period is even more than 1 day. Do you think that's really enough? Do you want me to increase it, or do you want me to keep it as it is, or do you want me to make it just like 1 hour, 2 hours?
I did notice that on Gradescope it did say late due date, but
yes, that's late. That means normal exam is this amount of time, but late because some other people, they have a time difference.
yes.
Some people is not located here in the United States because of the COVID-19.
So wait, so the true due date would be that late due date
It's still I take it and it doesn't affect you.
Oh, okay. I see. So it was more than a day.
Yeah.
It was about a day, yeah.
Yeah, it's a day and a half, maybe. No, it's even more.
I thought that system worked pretty well.
Okay, I mean, do you want more than that? I mean, I can give you 2 days.
Well, more time is always better. I mean, yeah.
Yeah. Okay, I will make it 2 days.
It's whatever you feel, Professor.
I mean, honestly, if I'm in professional, let me tell you something. I hope that you guys don't think that I'm harsh or something, but what I want to say that the whole entire lectures I made, or the whole entire material I'm teaching you, is based on the industry perspective. And in industry, normally, managers, they don't, how to say, they're not that really friendly as you think. They are still looking for results, right? And I'm talking about the exam. So I'm saying that first of all, maybe I can repeat the whole entire story. So first of all, the exam, I'm saying that let's say that you did not really great in the midterm 1, right? But you did really great in the midterm 2, right? Then what I'm gonna do, I'm gonna match it. So the number 2, it will be the official midterm for you. Number 1 will be taken away. But let's say that you made really bad in 2, but great in 1. I'm not gonna match it because you didn't show me any improvement, right? So I will just leave it as it is. I will just take this one and add them to each other, right? So there is a chance for you to improve yourself in the midterm too. And the same thing for the quiz. Let's say that the quiz one, you didn't do great, but then, in quiz two, you did really great. Then, I will consider quiz two is your official quiz. Okay, so Tristan say, Tristan said that, if did you give us 2 days, would you be given more problems? I don't think so. I mean, this is the only thing that I'm thinking about is trying to extend time for you. That's it. But I'm not gonna make it more difficult, Okay. Another thing, what exactly we need to learn in the 3300? 3300 is based on what? 2300. If I know 2300 very well, 3300 for me it will be easy. That makes sense? Why? Because 3300 is just a bunch of syntax, right? So if you understand design, it's pretty much easy for you just like to pick up the syntax. By the way, another thing, there is no shame to open Vivado and try to answer to see whether that your answer will come out correct or not. That makes sense? And end of the day, when you you will leave the Calpoli, right? And your manager, in the company, or let's say that you're grad school and a student and you're working for PhD, you can search, right? You can look for something, but you don't steal. That's the whole idea, I mean, cheating without understanding what is this weird, So another thing, when I say that notations, right? Like, I know that, you can come and say output Z, and then it automatically Vivado will consider it wire. But, it is wire. You have to say wire because, we are in the beginning of the 3300. So that means, you have to learn this is wire and the other one has to be registered. So you have to put it wire. That's proof that you already attend and you watch the videos and you understand what I'm saying. So, be sure, to follow the course notation. That makes sense? What exactly I need from you to learn? I need you to understand what is timing. How can you calculate timing? How can you know there is a critical path? How can you identify passes? So the question number one, for instance, there are 5 passes. From where? It came from the lecture, one of the lectures. It was the same problem, if you guys remember. And there was just a block of the combinational circuit in the middle. Do you guys agree? The only difference, it was what? This block, instead of saying that, combinational circuit maximum, minimum, this amount of time, you will calculate it by your hand. That makes sense? Right? So shall we go now through the midterm? Hello?
Yeah.
Okay.
Yep.
Let me see. Excuse me. Where's my Zoom? How is going with the lab? Did you guys fix it?
I have one problem, or just for the test bench for like the top module. Since the refresh counter is supposed to refresh every like 10 milliseconds or so, does that mean we have to make our simulation that long? Because I did it and it was eating up like, or it was taking a really long time to simulate.
Oh, let me think about it. That's a very good question. So, let me do one thing. One second. It's
Sometimes when I have like a long simulation time or
Yeah.
when it's calculating, it's usually because there's I think there's like an excessive loop that's running too long, too many
Correct.
times.
Correct.
So if you're using loops at all, you might want to check if those loops are running at the amount of times you want them to run and not anymore.
Well, I mean, behavioral, because if we want to test the refresh counter, we need like at least, let's say like under 1 second, not 1,000 nanoseconds,
Correct.
because of how many times the clock divider in the SSD gen divides it by.
Yes. I can, do you have like did you set up a meeting with me in what's called on Calendly?
Not yet.
Yeah. By the way, congratulations for Lewis. Good job, by the way. Thank you. Okay. So anyway, back to the future, right? So what is the future? What is the, we have 5 questions. We said literally show all your work, answer without supporting work will not be given credit, right? So here, what it says here, identify static timing passes. We said 5. And basically, you can find this in one of the lectures. I already give it to you. Which one? I can give it to you. I give you the name and everything, Courses, it was in the 3300. And it was timing. And in the timing, it was, I think, number, I'll show you. Here, it's in a slides lecture 7, slides number 8. So maybe what I can do, I can just go here and say lecture 7, slides number 8. This guy. Is it the same thing or not? Everybody agrees me?
Yep.
Yep. So this is from the lecture. So first question is a straightforward. Second question is based on the first question. What is the difference between this example and the one in the exam? Somebody tell me. Lewis, tell me.
The combinational logic is not defined in an exam.
Yes. So how can you solve this? Based on what? Based on the one part also I mentioned somewhere else, which is the critical path, right? So for instance, excuse me, if we go here, you open there, what was the critical, where is all this? What was what is the circuit inside this? What is the circuit is? 1 bit full adder, right? We made the 1 bit full adder before. Do you guys remember? How many of you remember the 1 bit full adder when we made the design using NAND gates?
Yes.
So you know what is this, right? So you just use it and then use the same equations of the lecture 7 here, excuse me, for calculating the maximum frequency, which is what is the longest path, right? And from there, you will be able to figure out maximum frequency. So you got the maximum frequency, you figure out, what is the critical path, the longest one, and you figure out how can you calculate 1 bit full adder. So that's pretty much, from whatever we already learned so far from the 3300. So far, is there any question? Good. Now we're gonna move to the next question in the midterm. Next question in the midterm. This is something we have seen before. Everybody agree with me? This one is what? Negative skew. Negative skew effect on the next flip-flop. It's affecting this. Everybody also agrees with me about this one? This one is a very clear example, also came from what? From the what? From the lecture, right? Let's see, where is it? I remember it was in here. Let's find it. Here. Right? And here are the equations we're gonna use. The first rule and the second rule. What is the difference between of this part and the one in the exam? You just need to calculate what? This combinational circuit. How can you calculate the combinational circuit? Based on what? The same trick we learn in one bit for others for the critical path. And the knowledge you already have in the 2300. That makes sense? Hello? Yes. What about the rest of the people? I would like to know whether that's, they have seen this before or not. Yes, so that's why, I'm asking everybody, please, I understand that you guys have a lot of stuff to do. And I completely, I was a student and I know it's really hard, especially with this COVID-19, but, just promise me to do your best and to look to the materials. I'm giving you all the material, which is the standard for the, why is the whole time never take into the account in number one? Where is this one in number one? What do you mean? You mean in the first question? Oh, yeah. The skew is the one affecting the whole time and setup time, because who is passing the clock? Wire, right? So your clock is pushing into it, right? So think about it. What is the source of the clock? What is the problem we have? The problem is you already have some time here, some time there, and those for the input, right? Before and after the clock. So who is actually the problem we have? The problem is from what? The clock itself. So there is no big problem you can find in the whole time for the first question. The problems will come here. That's why if you remember in the skew, we said, one of the positive skew will affect on the setup time and it will make it worse for the whole time. While in the negative skew, the setup time will be really worse, while the whole time will be what improved. Do you agree with me, Andrew? Yeah. So if I'm a hiring manager, I like, for instance, all my ECE3300 students to be joining Intel. How many of you like to be working for Intel, for instance? Are you guys in favor of Intel or AMD and stuff like that? So if one of you like to join AMD or Intel, right? So they have to think about one thing, right? What type of question they ask even in interview? Imagine what? Timing. The first, Intel have 12 exams. If you pass all of these 12 exams, you will get inside Intel. You will be a digital engineer in Intel. First exam, it's about, flip-flops, how the flip-flops work, how can you build up-down counters and stuff like this. Second exam, it's about timing. Whole time, setup time, how can you identify critical passes and stuff like that. Third exam, it's about what? Combinational circuits. Fourth exam is about sequential circuits, with combinational circuits. And then the rest, it will be about designing complex problems. What we are doing in the lab is complex problems. Like, you have dividers connected to up-down counters, then, it's connected to the 7-segment display, then it will proceed something. That's called complex problem. So you are an undergrad. If you learn these tricks, you will be ready for what? Joining Intel, or joining IBM, or joining even MSR. How many of you heard about MSR? MSR. MSR is a stand for Microsoft Research Center. Okay, so MSR, it's the research center in Microsoft. And they're hiring digital engineers and software engineers with digital knowledge. So that's why I want you, please look at this. Do you want me to give you like a copy of my old 2300 so you can look at even the materials? I can give you all of my material for the 2300. I will put it tonight on the I will put it tonight on my I will put it tonight on the course documents. So you can even look at it, and if you have any question, there is no shame. We are here to learn. Just tell me, Professor, can you please repeat this part? Maybe I didn't catch this part in 2300, so I can, help me and I'll help you. That makes sense? Okay. So now, first 2 questions we are done. It's proven that it's already in lecture 7 and 8. The only trick is basically identifying critical path. And last lecture before the midterm, I showed you how can you convert gates to NAND gates. Everybody remember? And that will be enough for you to use it. So you can build your circuit normally. And after that, you will take whatever, from that lecture and you just put it like in a blocks. And then you will look what is the long pass and you just write it down. Sounds good? Now let's move to the third question in this. This one, I noticed a couple of you actually give a very brilliant ideas, which I really respect. Like, some of you look at the perspective of, using the general idea of the clock divider. How many lectures do you guys remember we had for the clock dividers? We had 3, right? One, it was using the PLL, right? So the PLL is normally how it works. It's basically, you have a black box block using some ASIC analog circuit on the top of the FPGA for magnifying the maximum frequency or even attenuating the maximum frequency. That's one of the solutions, but this is not the solution because at the end of the day, I'm asking for writing Verilog, right? The second approach is basically building a counter and you select which bit is associated with it. If it's the outputs clock, it's basically based on the some equation wise of this. The third approach, it was the last approach, and I believe also, Mario were talking about it, right? When you said, how many cycles per on and off of the new clock will be identified, then we came with a comparator comparing, and if it's equal, and then enable of the flip-flop will be going in, and you will push the desired output, and the output will be propagated. And that was the last lecture of the clock dividers. This specific one in this exam, it's a piece of cake. Somebody tell me why? Because the following, 200 megahertz divided by 128 is what? Thank you. We're done. That's it. So we said if we have a counter like this, here is the new clock, here is reset, and then here is the output. So that's basically going to be our circuit, right? One of the things I noticed some of you are confused, which is fine. We are learning here. What does XDC 100 megahertz mean? Somebody tell me, from your point of view, from the practical life we learned so far, what is this 100 megahertz came from the board? Came from where?
That's the standardized clock of the FPGA, right?
Exactly. But what the circuit inside the board is doing this?
What inside the board is providing that 100 megahertz?
Yes.
That's like the crystal, right?
Crystal, exactly.
Yeah.
So that doesn't mean that every single board in the world will be 100 megahertz. That makes sense? Maybe some boards, the crystal will be generating 400. Maybe there is another board, I have a board here is Alveo, is generating 1 gigahertz crystal. So the XDC will be 100 gigahertz or a gigahertz. Then the PLL will make it up to maybe 100 gigahertz. You know what I mean? So the 200 megahertz is your input. There is no relation at all with XDC. So you don't need to instantiate PLL that it will convert 200 to 100, and then from there you will work on building your circuit. Make sense? So this is a little bit, maybe you guys were confused, but maybe, but for now, I hope it's very clear. So, I have 200 megahertz and I have my input is what? 1.563. So that means the output. So that means, I need to build a counter, and this counter, how many bits? Somebody tell me, 8 bits. Right? So gonna be here what? 1, 2, 3, 4, 5, 6, 7. Let's make it 7. That's fine. So basically 7. So gonna be from 0 to 7. So gonna be 8 bits. Or you can make it even 7 bit, 0 to 6. That's fine. Then here is my new old clock, and here is a reset. Then the first wire is 2 power 0, right? But it's not completely 2 power 0. It's 2 power 0 plus 1. So it's going to be here 1. So, I mean, bit 0 in the counter will be the current F divided by 2 power 1. Then, 1 is going to be F divided by 2 power 2. Then B2 is going to be F divided by 2 power 3. Then, B3 is going to be F divided by 2 power 4. Then, B4 is going to be F divided by 2 power 5. And then B5 is going to be F divided by 2 power 6. Then, B6 is going to be F divided by 2, 7, and so on. That makes sense? Which one do we need from your point of view?
B6.
Right? So that means, if this counter is called counter like this, you can just write a very easy code, say that it's a counter. And then, you will take the wire of the count 6 and you consider the new output. Then you are done. So you don't need, for instance, to use the same lab tree, for instance, with the multiplexers and 4 switches or 5 switches, because I'm not asking for multi-clock domain. I'm asking for just one wire representing this output. That makes sense? No, Shad. Yeah, this is confusing, and I agree with Shad to ask this question. And 0 is not 2 power 0. No. You know why? Because, if you remember, this is synchronous counter, right, Chad? So that means, the changes will be recognized every positive edge. From positive to positive, it will be on. Then, from negative to negative, it will be off. Then from positive to positive, on, off, and so on. So that means actually in bit 0, you're actually dividing by 2. You know what I mean? If you are asynchronous, then, the story would be different. So pretty much you just need to write a behavior. And here even, I didn't say write it with any model, right? I just wrote, write a code, right? So, I mean, how many of you know how to write a code for counter? It's pretty much easy, right? You can just go ahead and say that, I need to add, do I have extra page here? I can write here. So I can just say, I can just write here module, right? Clock, div. And then I open like this, and then I say here input, clock, input, reset. Then I say output, wire, and then I say clock new, for instance, and that's it. Then I will come and say that, always at positive edge of the clock, then, or positive edge of the reset. Then I say here begin, and then I go here and say end, right? Then I will go ahead and say that, F reset, that means it's high, right? So gonna be what we need. Also, we need here, we need here reg 6 to 0 maybe. And then we say here count. And then, if this reset happens, we'll just say count is equal 0. Then, you say else count is equal count plus 1. And everybody know what is the trick of the blocking, non-blocking, right? It's also one of recorded lectures mentioning this about here, right? Because, we are in sequential circuits. Then, I will just go ahead and say, I'm done. This line is done. Then I will just say assign. What was the name of this thing? It's called clock new is equivalent to count. So we finished. If you do this, you will get the 25. And then you make a test bench. Maybe, if you give me a test bench, but the RTL is wrong, think about it. How I'm gonna treat you? I mean, how can I put a grade for this? Like somebody's asking you a question, find 2 numbers to add, but be sure one of them is 2. So that means, your answer, it should be 2 plus 3 is 1. But, if you give me 4 plus 1 is equal 5, you will get 0, unfortunately, right? Even you're gonna give me answers 5. So stuff like that, you have to be careful with it. I'm sure that we are learning, and over time everything it will be clear. So anyway, if we move forward, test bench is pretty much straightforward, right? You just instantiate this counter thing that we call what did I call it? I call it clock div, right? So clock div, I'm gonna instantiate it in clock div TB, whatever, and then I will just start pushing the clock, and that's it. I don't need to even write anything in the initial block. I just need to make forever, and I said, forever, and then think about it. This 200 megahertz, so you have to flip it in time, and then you divide it by 2. Then you will know the time of the period, right? That makes sense. Everybody agree with me? Hello. So it's straightforward, right? Anyway, now how many questions do we have? Oh, we have 4, right? So I mean, so far, we didn't take that much time, right? So let's go to the last one. So what is the last one? The last one is say that write the RTL and the test bench for the majority encoder, basically. And you already have 5 inputs. So what is majority encoder? Majority encoder is like this: 1, 2, 3, 4, and 5. So that's basically, let's call it I0, I1, I2, I3, and I4. And I just have an output, and this is output, call it something. Let's call it match. And then, the output, let's call it OB. Use what? Use structure modeling, right? So structure modeling like and, or, and so on. I noticed some of you already made it like big or, and this is not recommended. Also, I noticed also some of the answers have a star. And I believe in one of the lectures, in the recorded lectures, I mentioned that, avoid the stars, because when you will go for whole entire synthesized environment in Vivado, it might actually remove some desired signals and alter it with undesired signals, and then timing issues will happen. Do you guys remember this? Do you remember what I said, or you don't remember? So, Luis, you remember? Thank you. So anyway, what is the way that somebody will solve this problem from your point of view? Somebody tell me. Give me an idea. What should I do?
A truth table.
Hmm?
A truth table.
Correct. You're gonna make a truth table, and then most of you learn up to 4 K-map, right? So what? We can be tricky, right? What we can do, I can tell you a trick. You can make 4 K-map, and the last bit will be a multiplexer like this, and this is 0 and this is 1, and this is the bit control, and that will be the output, which is OB. Do you understand what I did here or no?
Yes.
Okay, maybe Anish, I can show it to you. So basically what I did here, think about it like this. I have five inputs majority encoder, right? So let's call it what? I4, I3, I2, I1, I0. Do you agree? So how many states I have in this table from your point of view? I have 32, right? So gonna be here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, then 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Do you need to make all of those lines? You don't need. You can just make 16th, and you just make here an aside I4 when is 0, I4 is 1, right? I mean, there is multiple way to do it. And then I go here and just flip it with 0, 1. What the heck? What did I do? One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Then here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Then here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Do you see what happened now? So if you notice, if you look at it very carefully, this table, it can be two tables, right? One when the I4 is equal 0, one when the I4 is equal 1. That makes sense?
Yes.
That's it, we finished. So basically, we're gonna look here, for the OB, right? We are looking for majority 1. I didn't say what majority is, so you can just assume majority 1s, right? So look at it. So gonna be majority 1 here. It's gonna be by default, that should be majority 1. So it's gonna be here 0. I have 1 compared to 0, so it's gonna be 0. I have 1 in front of 0 is 0 still. I have 2 in front of 3 is 0. I have 1 in front of 4 is 0. I have 2 in front of 3 is still 0. I have 2 in front of 3 is still 0. I have 3 1s in front of 2, 1. I have 1 is still there, 0. 2 is still 0. 2 is still 0. I have now 3 gonna be 1. I have here 2 is still 0. I have here 1. And I have here 3 gonna be 1 as well. And I have here 4 gonna be 1. Right? So now what I did, I already finished the first K-map I'm gonna be working with. This K1. Then I would change my color here so we can have more fun with coloring. I don't know. So basically here, 0, 0. Here is 0. Here is 1. Here is 0. Here is 1, 2, 3. In front of 2, gonna be 1. Here is more, gonna be 1. Here is more, gonna be 1. Here is 0. Here is 1. Here is 1. Here is 1. Here are more 1. Here are more 1. Here is more 1. Here is one more 1. And they're gonna be my K2. Then now everything looks clear. Super. So now I will just go ahead and make the first K map. 1, 2, 3, 3. Then I will go like this. Everybody know that K map, it should be from the left to the right. Otherwise, you're gonna go in something that's called orthogonal K map. So you have to read it like this. When I read it like this, it's gonna be what? It's gonna be I4, I3, I2, I1, right? I made a mistake. I4 will be excluded. So basically, you're gonna clear this, clear. So basically, I'm gonna write here to be I3, I2, I1, I0. Where is I4? I4 will be controlling multiplexer. Because see, in this case, this is 0, that's a K-map. This is 1, that's another K-map. Okay, now you just need to fill it. So gonna be 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. They're gonna be 0 location, 1 location, 3 location, 2 location. What is this? 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. So far, so good. We'll just take it literally from the table. So gonna be here, we are just looking to the K1, right? So location, when it's actually 3 1s and 0, that means 7. And the location when it's gonna be 1101, that's gonna be what? 11. So gonna be 11. And location 13, 14, 15. 13, 14, 15. That makes sense? Anything else in this table will be what? 0. So we're gonna put here what? 0, 0, 0, 0, 0, 0, 0, 0, 0. So far, so good? Any questions so far? Okay. Now we're gonna write what? We're gonna make it something that's called OB1. So OB1 is equivalent as a function of I3 and I2 and I1 and I0 is what? It's gonna be this group, and this is a group, and this is group, and this is group. So we have a full groups, right? So the first group is gonna be what? It's gonna be I2. Yeah, it's gonna be I2, I1, I0. I1, I0. Or with the second group will be I3, I1, I0. Then the third group will be I3, I2, and you go up here, it's gonna be I0. And then the fourth group will be I3, I2, go up here, it's gonna be what? I1. You can be tricky a little bit, so you can just come and say, clear it up a little bit. So it's gonna be what? It's gonna be it's gonna be I1, I0, and then I2, or there was I3, and then I2, I3, and it's gonna be here I0 and I1. So you finish OB1. You're gonna do the same thing for the second K-map. Okay. So the second K-map is like this. The second K-map 1, 2, 3. 1, 2, 3. Then I3, I2, I1, I0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1. I think I'm mistake, right? Sorry, 1, 0 here, and then 1, 0 here. It's gonna be 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. Okay. Okay, then I will just go like that and close like this, and then I will look to the second part of the table. Second part of the table said, second part of the table, this guy, right? This guy is in front of what? 3. 3. So 3 will have 1. Then this guy is 5. This is 5. Then this gentleman is 6. Okay, that's here. Then this one is 7. This one is 7. Then you have, what is this? 9, 9, 10, 9, 10, 11, 12, 13, 14, 15, 1. 9 to 15. So it's gonna be 9, 9, 10, 11, 12, 13, 14, 15, and so on. Anything else is gonna be what? 0, 0, 0, 0. So far, so good. Are you guys following me? Okay. Same trick. You're gonna do the same thing. I don't need to do it, right? I will just leave it for you so you can actually doing it practice. Anyway, you will generate OB2. Then are we done? No. What will happen? You will propagate OB1 here, and you will propagate OB2 here, and you will take them into a multiplexer like this, 0 and 1. And who gonna be the controller? I4. And that will be the final OB. And when I4 is 0, I'm still electing this to be the output. While when is IB4 is 1, I'm selecting to be this output. And you will just write a piece of code for the multiplexers, and a piece of code for this, and a piece of code of that. That will be around, I think, 10 lines of code, or maybe up from 5 to 10 It depends on whatever you're gonna use, using the structural modeling with bunch of analog. Any questions? Is it clear? Super. So from whatever we learn now today, the whole thing is based on what? The lectures and materials we have, plus knowledge from the 2300. That makes sense? Do you guys agree with me, or you don't agree with me? So you promise me you do your best, please. Focus on the midterm 2 and quiz 2. You do great in both of them. Forget about midterm 1 and quiz 1. Sounds interesting, right? But unfortunately, I'm gonna look at individual. If I find you was doing really great in 1, but you start going down in 2, I cannot help. So please help me so I can help you. Sounds fair?
Yes.
Perfect. So we closed here. Do you want me to send you to put a copy of this in the Blackboard? I can put this on the Blackboard as well. This notes, I can send it now to you guys. Send email, send it to myself. Maily. And once we finish the lecture, I will just put in the Blackboard. Okay. Now, do you guys remember what we was talking about last time? We were talking about what? Finite state machine. Correct. How many type of finite state machine do we have? 2. Somebody tell me what those guys are.
Melee and more.
Correct. Melee and more. And in the lecture that we talked about, that was me. I was sending some stuff to myself. Here. So melee and more, Eduardo is correct. So melee and more are the 2 different modeling for describing finite state machine. Pretty much finite state machine, it's a way of thinking. So that means, you are gonna use behavioral modeling. And, you should have a very good skill in coding. And I believe all of you already had experience with C, right? Did you guys already have a C as a course? Yes, so if you know some C, that means C and C++ and C#, whatever, if you know some programming perspective, finite state machine is a piece of cake for you. So pretty much, you have a skeleton, and you have to think about whether this finite state machine, it will be defined as synchronized or asynchronized. Do you agree? So one of the way to build a finite state machine is the following. I will build a body here, and this is going to be combinational circuit. And here is the input, here is the output. But because, we are using a kind of recursion, that means, the previous and the next going in a serialized way. So that means I have to go ahead like this and pass it to here. There is no way for you to do this without adding a delay perspective. So adding delay perspective, we're gonna remove this, and instead we'll take the delay and just put here a delay, and that will be moving up like this. So the delay here, so the present will be, here's the present, here's the next, and then you will keep moving back and forth with the input. You will identify what is the output. So this is the finite state machine. So the skeleton in front of us here is showing that I'm going to make the delay here of the next. Look at this part. I'm actually highlighting. This is exactly the part I'm actually highlighting in front of you on the draw part I made, right? Then this part, the combinational circuit part, is that part as a combinational circuit. That makes sense?
Yes.
So this is basically what we need to know. If you learn that, then you're done. How are you gonna make them? There is multiple stories, right? It's organizational. So, what did we learn so far as a trick from the Verilog? I can use parameters, I can use lookup parameters, I can use define, I can use, whatever to make my life is really quite easy, right? So popular way to do is basically to use define, so it will be easy as humans if you have a huge number of finite state machine to know which one is what. That makes sense? My question to you guys, while you are studying C, did you learn how to use include, right? Do you remember the include file? So organizationally, we can make a new file in Verilog and we just define states. And then, we go include it in the new file. That makes sense? There is a function in Verilog called include. So you can just go ahead and say that include. And then, you put here the track of the file is holding define, and then automatically all of these defines will go there. But for making it easy for us now, we'll just stick in the top of the module, we'll just put all of the defines. So to stick with an example showing to us something running, if you guys remember in the 2300, when we started learning about sequential circuit, we learned about something called sequence detector. How many of you heard this term, sequence detector? You didn't take it? When did you take your 2300? You guys mind if you tell me the name of the professor? I'm just, it's up to you. That's fine. Anyway, yeah, so sequence detector, it is, what does it mean? Let me tell you a story. In COVID-19, right? COVID-19, how they figure out that, that person is already infected or not? Tell me. Let's think about it. Let's just think. They have a sequence of what is COVID in DNA, right? And they will bring the whole entire DNA of you coming from I'm sorry to say, from your mucus, right? And then, they will put it in the sequencer, that's something called sequencer, and they will start looking into your whole DNA coming out of this little itty bitty tiny sample out of your mucus, right? And then, from there, they will come and say, oops, Muhammad had it. So they need a sequencer. So this sequencer is like this. It's a circuit. You push sequence and you push your pattern, and you identify whether that you already have the pattern or not. That makes sense? Who can help us to do this? Digital logic design. So let me grab here at pages. Okay. So we said, here is a circuit like this. Here's sequence. Here is pattern. And here is the output. So far, so good? That makes sense? So that sequence detector, sorry about that. Go. Yeah. The sequence detector can react in two different ways. One is called with overlapping, and one without overlapping. Before I go into this, I will tell you a story. It's a very interesting story. So, how many of you heard about DNA? So imagine that in a computer, we have two things, right? 0 or 1, right? And the whole entire 0 or 1 is a business of switches, right? So, you know, you are turning on switch, you are turning off switch, you are turning on switch, you are turning off switch. Everybody agree with me?
Yes.
Okay. Human DNA is a little bit different, you know. Humans also, you know, we are programmed. But our program is coming in something that's called DNA. So this is our program. So, you know, somehow this program in your blood, every single cell in your body, no matter it's in the blood, no matter it's in the tissue, no matter in organs, you know, it's DNA. You can find DNA in your hair, toenails, you know, nails of your hand, whatever, you know. This DNA are carbobases. It's a, you know the carbons, right? So there are 4 shades of the carbon bases. Those are called A, T, C, G. Okay, A, T, C, G. And the representation of them consider a program. What does it mean? So if I find in a certain truncation of your code is sended, is right like A, T, C, C, G, A, T, C, C, G, A. This can be translated because, in computer architecture, for instance, you know, we look for translation, right? So like, you know, this code, it means something, right? It means that launch a rocket, or mean, you know, open a speaker, close microphone, whatever, right? So that can be, for instance, you know, a message to the body to what build a new organ, and this organ is liver. And then there was another piece of code written in this long strip. It said that, you know, C C T A C C G A T C A G, whatever, right? Oh, that mean, you know, create your kidney, and so on. You know what I mean? So that means the humans are not 0 and 1. Human are different levels. Human are 4 levels, right? So how many of you remember chapter 1 in 2300, number system? Do you remember number systems? In number systems, we are considered base 4. We are not binary, right? But luckily, we can be a binary because we learn the conversion, right? So I can come and say I have A, T, C, I have T, C, G, right? Scheiße. No, I can make a table and say I can convert from 4 base to binary base. So I can just write here 0, 0, 0, 1, 1, 0, 1, 1. Then I can just replace those guys with the binary equivalence of it. Do you agree? So still I can convert myself to binary, but 2-digit for each digit coming from the human perspective, right? Now, if I go like this, I come and say that 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1. Instead of A, C, G, A, C, T, C, C, G, A, C, T, right? That makes sense? Do you guys agree what I did or not? That's a way of something is called what? Encoding. And we learn what is encoding, right? So in that case, I can come and say that, you know, I can build a sequencer as a digital engineer. is the following. I'm looking here, and I say that, you know, Muhammad is looking for this pattern. 1, 1, 1, 1, 1. This is a pattern Muhammad is looking for. So I'm gonna take it one by one. So I have here a clock, and every single clock I'm pushing one single bit, and I'm looking, right? So for instance, you know, if I'm not looking for overlapping, right? What I'm doing is the following. I find out that, you know, I have 0. Let's say that, you know, let's have a realistic story. So gonna be 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, something like that, right? So I found 0 in the first one, right? Oops, but the first one is 0, 1. Nope, still I'm gonna stay in location 0. And then, you know, I found still 0. Still I'm gonna stay in location 0. Oops, I found 1. Perfect. So I found 1, but still I didn't find the rest. So I stick in 1. Then I found here 1. Perfect. So I find 2 of them, but still I didn't get anything, right? Still. Then, oh, I found 0. Oops, I returned it back to 0. And then I found 0, still returned it back to 0. I find 1. Perfect. I found 1 again. Then another 1, but it didn't continue. So I will move forward. Still, you know, my output till here is 0. Then, yes, I found 1. Great. I found the second. Great. I found the third. Great. I found the fourth. Great. Oops, this is 0. It ended back to nothing. So, you know, everything is still 0. Then, great. I found 1. Super. I found 1. Super. I found 1. Great. I found another 1. Great. I found another 1. Super. So from this one, the output is 1. So that means anything from here is 0s, but from this moment, I found 1. Overlap mean what? Overlap mean that, you know, those guys with the previous is still making 1, 1, 1, 1. So that means my output would be 1, 1, 1, 1 like this. But if I don't overlap, that means I can clear up this, and I say I return it back to 0. And then, you know, I still have 0 here, 0 here, 0. Oops, it's returned it back to be 1, and so on. So far, anybody understand what I'm saying?
Essentially, that it by making it into binary, we're able to apply digital logic to solve this biological problem.
Yes. So yeah, I mean, I've been working for this while I was a scientist for Illinois, and I already have a paper. It's heavily cited about this. It's building a processor for the DNA sequencing.
Oh.
Okay, and it has a 44 processor on FPGA. So what is the way for you to design something like this? It's easy, right? How many sub-patterns inside the pattern? 1, 2, 3, 4, 5, right? So that means how many states I should have? I should have S0, and I call this initial. Okay. Then S1, that means I found the first location. And then S2, I found the second location. Then S3, I found the fourth location. So here is the first. There's 2 locations, 3 locations. How many we have? 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. So this how many states I should have. Okay, so that means in total I should have 6 states to solve this problem without optimization. Then I will need to do what? A diagram, right? So, you know, do you guys remember the diagram for finite state machine? State diagram?
Yes, the diagram with the bubbles.
The bubbles, exactly. So was it, you know, it depends. Do I want it to be melee or more? I can make it melee, I can make it more. Let's make it melee first, right? So I have 6 states, right? S0, I have S1, I have S2, I have S3, I have S4, and I have S5. Everybody agrees me? You know what? I'm not really great in drawing by hand, maybe. But everybody can understand what is written in front of them, right? Now, I'm standing here, right? This is my initial. So my standing here said that, you know, I am going to myself like this. What does it mean? If I find the first input 0, my output 0, and I'm going to stick at 0. Who is actually a good candidate for this, these two inputs? You agree? Then when S0 will go to S1? In one case, when the first input will be 1. So here is 1. And still I'm 0. Super. Now while I'm standing here, is my next going to be 0 or 1? If my next is 0, I'm going to back safely to who? To here. So going to be 0 and 0. But if it's 1, oh, good. I found 2 of them. And I'm still looking for more. Then I'm here. If I am 0, I'm going back to this. So going to be 0 and 0. But if I am there, I will just go like this and say that, you know, oh, perfect. I found output still 0 and 0. So I found here 1, 2, 3. Still have more, right? Then I will do the same thing. If I'm still didn't find, so going to back to here to be 0, 0. But if not, I will just go here to be 1 and output still 0. Then, you know, the same thing here. It's going to be 0 and 0. But if not, I'm going to go here to be what? 1 and 0. Then here it depends. Here is this overlap part. So if I find an S5 1, then I will go like this all the time to be 1, 1. So that means I'm actually overlapping. If not, I will go back here to be 0 and 0. So this part is overlapping. That makes sense? But if I'm not overlapped, I will just remove this part. I will just be here 1. And then I will just move forward to 10 back to look to the same sequence from scratch without remembering that I already have 4 others in the old data. The question here, you guys are following me and understand what I said? If it's not clear, there is no shame. I'm here for helping. Go ahead. I'm waiting for the rest of the class. If one of you is not clear, you know, I can make it. Okay. Okay, so the simplified one, it was the one I showed to you here, right? This is a simplified one. As a point to mention, you know, the style I use here for describing the finite state machine is what? Mainly. Not CBB, by the way. Right? That's a mainly finite state machine. Sounds good? The one in front of you here is different. The one in front of you here is looking for just like this, 2 patterns, one like this. Right? This is the pattern we are looking for. That's why we have the initial is 0 and then 2 of them. That makes sense? Let's see, right? The one, and then, you know, this description is not mainly, this is more. Why? Because every state itself is defining the output, and the arc just have the input information, while the transition in melee describing the current status of the output regarding the input while I'm moving between the states. Just like clear information to you guys, melee is more for optimization purposes, while more synchronizations and make it easy for you and just like work. So every single model, it has its own application. Sounds good? What tools we know 20300, we know what is happening. Now we know it's the rest is going to be a piece of cake. It's just using what knowledge we have in the syntax writing of Verilog as a Verilog HDL, which is stand for Verilog as a hardware description language. Okay. So if we go there, you will just go ahead and find the code, right? The code is written, is very straightforward. So I use a define to define the states to make it easy for me while I'm programming. And then, I'm expecting in the finite state machine to have clock and reset because it has a sequential perspective here because we are making this delay part, right? Then, there is an input and output, all right? Then, we define the in and out, and then, we define the output to be a reg because, they're going to be associated into a state machine. Then, we go ahead into the next state and previous state based on also knowledge we learned from the 2300, saying that, how many states do we have? We have 3 states. How many flip-flops do you need for implementation? It's going to be 2, but 2 is covering 4 states. That means, there is 1 extra state I don't need. But this is the only realistic way to do for implementation for such a. Sounds good? So in that case, you just say here, always block if the reset happened. That means I'm starting from the state 0. If not, be sure next is going to be equal to the present state. Clear? Then you will move forward to the always block here, which is combinational circuit. Say that always block. So the input and the current state will be the one who is actually deciding what will be the next state. And from there, you say case statement is a state, and then, you identify your state using case statement. I have how many states? 0 and 1 and 2. If you like, you can make state 4 and say, nothing will happen, but don't branch to it. So you will avoid latches. Because do you remember when I told you that? You remember when I said in case statement, be careful, fill all your possible states, because in that case, you might actually cause the compiler to think that there is an extra state, and he can go in something that's called deadlock. Okay? So there, I said state 0, state 1, state 2. State 1, 0, I go inside it with branching, right? If enable is equal 1, so that means, I'm going to go from 0 to 1. If not, I will stay in myself in 0. And there, the same thing, I will go to 2, or I will just go back to 0, and the third one will be the same. This one in front of us is what? Overlapped or without overlap? Hello. Hi, everybody. So the state machine in front of us was overlapping or without overlapping?
Overlap.
Super, great. Yes, correct. So then, we need extra always block because, this is more, so, we have to define that when the state is happening, that output will be 0. When the state happening, the output will be 0. When the state happening, the one it will be 1. Have you noticed the whole entire thing is combinational? So that's asynchronous finite state machine using Mealy modeling for the sequence detector detecting 2 bits consecutively equal 1 with overlapping. That makes sense? Any question? Can you explain what overlap is more and more time? Yes, sir. Imagine the following, you have here 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, right? Now, I'm looking for 1, 1. Okay, Christian? So, this is 1, but this is 0. Output is 0, 0. Here is what? 1. First 1, still 0. Second, 1. But then, this is 0, returning back to 0. This is 1. So possibly this, but still 0. Oh, returning back to 0. And you will move forward up to here, right? And then everything here 0, 0, 0, 0, 0, right? Now, I found 1, 0. I found 1, yes, 1, right? If I'm not overlapped, that means, this one is 0. Then, this is 1. This is 0, and this is 1. This is without overlap. Let's see overlap, right? I'm here, I started to be 1, right? This guy we'll consider the previous one is the second one here, so gonna be here 1. This guy will consider this guy to be with it, so gonna be here 1. This guy will consider this one, gonna be 1. This guy will be considered the previous one here, so that's gonna be the output for the overlap. That makes sense, Christian? Other questions before we change the subject? Size. 1 second. Any other questions? Hello? Hello? No questions. Okay. So what I want you to do now, I'm not gonna, pumping you with a lot of material today. So what I want you, very easy, to look at this code and you will go program it using what? The verb, right? And you focus with what? With your lab, because you're gonna give it to me on what? On Wednesday. That makes sense? Sounds good. Yes, I believe. Yes. We didn't have extra labs, right? Because I give you more time. So to make it easy for everybody, there is one big problem in my code. I give it to you, and is in the assign. Enable out. Why? Think about it like this. I'm up and down, right? When I go up, that means 0 to 9, right? First digit, it go all the time with the time. Cycle. So the enable out all the time will be what? 1 cycle. So far so good, right? But then the problem will come from digit 2 up to 8. Why? Because digit 2, when it's 90, for instance, 0 will be iterating while 9 is standing 9. But 9 is issuing enable out to be high. So they're going to be high forever. So you will find digit 1 and digit 3 is doing what? Running. But that's not correct. So we need to do what? We need to get out of every single block, no matter what is the solution, tick. When it's C9, is a tick. Even stay 9 forever, just 1 tick. Same thing for down, right? So maybe you can make some tricks. One of the tricks you can make, you can take enable out with enable in and you end it with them, or you OR them with, or XOR them and you push them as a new enable out. Maybe. Or you can build a little combinational circuit. No matter what is 9, just one time it will be just giving you enable out. And for the down counter, when you will reach 0, the same thing will happen. That's it. And of course, who will be in the middle? The up-down signal. Does it make sense? Hello? Make sense? Okay, in that case, I would say thank you guys for attending the lecture. And as I asked you, please do your best on just revisit all the materials. And if you have any questions, I will be more than happy to assist you. And on the top of that, as I said, if you are doing great in the quiz 2, quiz 1 will be taken out. If you are doing good in the midterm 2, I will take out midterm 1. But other than that, the grade, it will be the same. So, I'm sure that all of you will do great because you guys are really great guys. Okay. So what I would say, thank you for the time, and I enjoyed, and I hope that you are also enjoying the course, and God bless you and stay safe. Thank you.
Thanks, Professor.
Thank you. Bye-bye.